So we'll change over at this point now to the session on functional safety systems, where we have 5 speakers lined up to talk about different aspects of functional safety systems for machine protection and personnel safety. Co-chair is Joshi Saji. Did I say that right? I'm sorry if I didn't.
Yeah.
Thank you. And I'll go ahead and introduce our first speaker. So a reminder to the speakers, 15 minutes is allowed for each talk, 12 minutes for talk, 3 minutes for questions. And we will remind you when there are 2 minutes left out of your 12 for talking. So I'd like to welcome our first speaker from CERN, Katrina Cizé-Sitz. She will talk to us this morning about network interface stress tests for the CERN radiation monitoring electronics. Katarina, sorry, please go ahead.
Thank you. Thanks for the introduction.
We can see your slides. Yes.
Perfect. Okay, thank you. So I'm working at CERN in the radiation protection group, working on the CERN radiation monitoring electronics. And today I'll introduce to you the ROMLib-EMO, a network interface stress testing tool for the Chrome system. First, I will speak about the CERN radiation monitoring electronics and about the Romulus communication library, which is the one that we are testing with that tool. And then the need for robustness testing. Further, I'll talk about the tool, ROMLib-EMO, and the robustness testing results that we have achieved with it. The radiation protection group at CERN is responsible for the radiological safety of people at CERN and around CERN sites. And for this reason, one of our safety systems is the Chrome system, the CERN radiation monitoring electronics, that are gradually replacing the currently already existing systems, Arcon and Ramses. The Chrome system consists of autonomous units with a radiation detector, mostly ionization chamber, and custom-made electronics. And they are configurable remotely via a SCADA-based supervision system. They're installed at different, mostly human-accessible areas. They can then trigger alarms in interlock in cases of dangerous conditions. The processing system of the Chrome measuring and processing unit, which is the detector and processing system, it houses a system on chip with an embedded Linux and a user space application in C running on it. And this application uses a custom-made C library to communicate with the SCADA-based supervision system called REMUS, from where it can receive around 150 parameters. And then it interfaces and passes the parameters on to the FPGA section of the system on chip that contains all the safety critical calculations and measurements, and also the decisions which trigger the alarms and interlocks. And this is in a fault-tolerant architecture, so all the safety part is inside the FPGA, and the software is more for the interfacing with the remote side. We have developed the Romulus library that has been introduced on Monday by my colleague Amitabh Yadav. It is used by the CMPU application and by the Remus server to communicate. It implements a custom protocol on top of TCP/IP, and it can be used to get real-time data and historical data from the CMPU. And also it can be used to write and read safety-critical parameters. And especially because it can write the parameters, it has to be really safe and robust. Robustness is defined as the degree to which a system or component can function correctly in the presence of invalid inputs or stressful environmental conditions. A robust system would always behave properly as expected, even in unforeseen operating conditions. It doesn't accept invalid inputs, and it also never produces faulty output when presented with unexpected input. And robustness testing aims at evaluating exactly this, at evaluating the response of a system to unexpected inputs. There are many different techniques that can be used, and what we use with our tool is fault injection on the network protocol layer. The functionality of Chrome has been already tested with several tools. And what we want to do with ROMLib-EMO is in particular to test robustness of the Romulus library itself and the user space application on the CMPU that uses the library. We want to increase, on the one hand, the availability of the system, mainly of the application, means the remote configuration then. And this we want to achieve by reducing the risk of application crashes. And we want to increase reliability and safety of the system by avoiding unpredictable system behavior due to invalid inputs. Invalid packets could arrive due to a fault in any of the software components. As we know, any software can always be faulty. So there could be a bug in the Romulus library or in the application or Remus driver that use the library that would cause an invalid packet to be sent, or maybe a version mismatch in the libraries, or also unexpected network traffic due to some network level misconfiguration could reach the device. And in all these cases, the application should never crash and never any unknown data should go to the safety critical calculations. We had already several tools to test the functionality, but they all use the Romulus library itself, which is only capable of creating well-formed packets, which is good for robustness in the normal communication between CMPU and the remote device. But we can't create intentionally bad packets. And therefore we had to create a new tool. And also we wanted to be able to have automated regression test suites. The RomLib has been independently developed from the C library based on the protocol specification, and it's written in Python. It can send and receive packets via TCP/IP, and then it can check for the expected response. Test cases can be defined as dictionaries of messages, or the RomLib features can be used to create more complex test cases with customized functions or modules. It's object-oriented, so it can be easily adapted for future versions of the protocol or the application. And the protocol messages and application parameters, they are generated from input based on the specification and then stored into dictionaries, which are used then by the functions and classes to create the packets. There are classes and utility functions to construct well-formed packets. They can be auto-completed so that it's easier to specify test cases. Also, the expected response can be, in many cases, pre-calculated automatically. And in particular, to test robustness, it allows us also to craft raw packets that do not conform to the packet structure or that do not conform to the application's parameter data types, and send this kind of bad input and then check the response from the device. So here I want to show an example how such a test case could be created. In this case, we send a set parameter command and we send good parameters, good packet structure. So we expect an acknowledgement from the application. And then we create automatically from the library a check packet that would read back the parameter, and we see whether the parameter has been stored properly. In the next case, we create a similar test case, but with a bad structure where the number of parameters is a wrong number because we have only 2 parameters here. So we expect the application to give a return code of inconsistent frame. And also we take the check packet from before to ensure that the application also didn't store the bad values. And then we can see in the output that everything passed. We have categorized our test responses and also the test goals according to the crash scale, which we borrowed from robustness testing of operating systems. We have adapted it slightly. The first 3 cases of crash, they are in our case regarding the availability. The C stands for catastrophic. This means the OS crashes. This does in our case not mean that the PL crashes, because this is in a fault-tolerant architecture implemented. So the PL is independent from the PS. The restart would mean that the application hangs and would require a restart, and abort means the application crashes. So in all these scenarios, the Remus side, the remote side, cannot communicate anymore with the CMPU. What is most critical for us are the S, the silent or safety failures. This is when an error response is expected from the device, but it doesn't get returned. So it means that the application would store some data silently that is actually bad data, but it doesn't inform the remote side. So one would rely on the system that has stored any data, and we don't know what exactly. This is definitely not safe. The last two categories, hindering, what we renamed as harmless, or functional, they regard cases when a wrong error code is returned or the expected error code, but the protocol specification isn't met. So these are functionally wrong, but from safety perspective, in our particular case, they are not critical. We use this test tool already since 2019 to run regression tests whenever we have a new software version. And we can see here that we found 20 safety bugs. We had 4 cases where the application crashed and 1 where it had to be restarted. And they have been, with each new version, solved. Some examples, what caused an abort was when very long packages were sent to the device, or when the data length was specified to 0. Also in a case, a floating parameter was set to a quiet none, and that caused to crash the application. And also when the interface was presented with many commands in parallel. Some scenarios that concerned safety was also when some invalid floating point values were stored by the application and then passed on to the PL, but the PL treats this as integers. So basically, we wouldn't know what kind of values are even stored inside the PL from user side, from remote side, because the software did not reject this bad data. And in other cases, when the package structure wasn't correct, then the application would be reading out of memory and would take some random data and interpret it as parameter and maybe even store it, even also without notifying the user. In total, we had 83 main test cases and 251 subtest cases that all only regard the interface. So there could be so many more test cases for functionality. This is just for testing the protocol structure and the network interface. We had 5 availability bugs and 19 safety bugs found. And what was really an advantage is to find these regressions early, or to find not only the bugs, but also to find regressions early. In general, these are the benefits of robustness, is that we can find much more faults than we can find with functional tests. So all of them had not been discovered with the functional tests. And the benefit of automated testing is that we can discover the tests before we ever put the device into a long-term test or into operation. And in future, we might extend this tool also with more functional tests, for example, with random inputs and a reference model for comparison. We might use it for hardware-software co-verification, where we have someone working on the topic at the moment. We might add security tests. And if we use continuous integration and development, we also would run this regression test automatically. Thank you for listening, and I'm here for questions.
Thank you. That was really interesting. I don't see questions in the Q&A. If somebody has a question, they can raise their hand. I would like to ask you, how long have you been doing the continuous integration testing, and how much overhead do you think this adds to your processes?
We haven't yet integrated it into a continuous integration system, but we run this test suite each time before we have a new software release. We run it manually. Okay. At the moment, it is relatively quickly. It's in terms of minutes. If you add more test cases, it would be more.
Thank you. Damien has his hand up.
Thank you, Karen. Thank you, Katrina, for the interesting presentation. I was wondering, maybe it was specified early in the presentation and I was not sufficiently focused. What is the bandwidth requirement on the network? What is the impact and the cycle time at which you have to output this data?
It's not very high, I would say, because we have the cycle time of the device is 100 milliseconds. So,
okay, so it's okay, and the network
also
is
it's
probably
not related. Yes, it can be anything. In fact, this is not so important because the real-time part is the one in the FPGA. Whenever you have new configuration received over the network, then the data is stored and passed on to the FPGA, but there is not a requirement when the response would have to be sent from the device. If that answers the question. So there's not really a bandwidth constraint in the remote side.
Thank you very much. very excellent talk. And we'll go to the next speaker.
Thank you.
Okay. Okay, so second speaker is Borja Fernandez Adigo. So he talk about towards the optimization of the safety life cycle for safety instrumented systems. Please start, Fernandez.
Hi everyone, can you see the presentation?
Yeah, I can
Yes.
see, I can hear.
All right, perfect. Thank you very much for the introduction. I will start giving you some context. Our goal in this project is to ensure the safety of our industrial installations. For that, one of the mechanisms that we have is to develop safety instrumented systems that are based on the functional safety standards. In the industrial process sector, the most appropriate standard that we have is the 61511. This standard provides what they call the so-called safety life cycle, consisting on 11 phases to complete the functional safety project, and all the requirements divided in 19 clauses, starting from the hazard and risk assessment phase towards the specification, the design and engineering of safety instrumented system to the management of a functional safety project. Based on our experience, to implement all the requirements from this safety life cycle is a very challenging task. It requires a lot of resources and is very time consuming. So what are our challenges and objectives in this project? The first challenge is to prove the compliance with the standard in our functional safety projects. For that, we have technical challenges and also challenges from the management point of view. We also have to deal very often with the constant evolution of particle accelerator and experimental areas, where those changes they may affect the safety of our industrial installations. In addition, we want to keep the traceability between all the phases of the safety life cycle when these type of changes are occurring very often. So what are our goals? As I said before, the goal is to ensure the safety, to develop safety instrumented systems that are complying with the standards. But in this talk, I will focus on the solutions to optimize the implementation of all those requirements from the safety life cycle. I will talk about some of the recommended methods that the standard tells us to apply, the integration of tools that they can automatize some parts of our safety life cycle, the creation of reports to standardize the documentation from our projects, and improve the management procedures to coordinate all the members of the project. In particular, I will talk about these three solutions for some of those more challenging phases. Let's start with the first phase, the hazard and risk assessment. The goal of this phase is to identify the hazards, the risk, and evaluate the necessary risk reduction, what the standard refers as target safety integrity level, SIL. One of the most popular methods to identify the hazards and the risks is the failure mode and effect analysis. In the sample that you see here on the right, a high temperature failure mode from a water-cooled system could provoke, for example, the electrocution of one of the person next to the installation due to, for example, a water leak in this system. How we can evaluate the necessary risk reduction? Well, the method proposed by the standard that we are using is the calibrated risk graph. This method consists in a schema like the one that you can see here, and together with these 4 parameters, the consequence of this specific failure mode, the exposure time of the person, for example, that is next to the installation, the probability of avoidance by any other means this hazardous event, and the demand rate of our potential safety function. By giving values to these 4 parameters, we can obtain the target SIL, the necessary risk reduction. And we need to apply that independently for personal, for machine, and for environmental protection. So based on our experience, what are the biggest challenges in this phase? The biggest challenge is to define the tolerable risk for personal and machine protection. This is what the standard refers as risk graph calibration. Actually, for personal protection, the standard gives some examples that eventually they could be applied directly to our industrial installations. However, for machine protection, there is no such a thing. The machine experts, together with the safety experts, they need to get an agreement with the approval of the management. Just to give you an example of some of the calibration that we have done for one of our projects, for the consequence parameter, we have calibrated based on the delay time or the down time of the installation. For example, a failure in one of our projects, a failure provoking a damage in a magnet of the Large Hadron Collider at CERN will imply a delay or a downtime of more than 1 month in the physics program. This is obviously something that is not tolerable and is actually the worst case scenario in our calibration. So what we have done to summarize for this phase? For this phase, we used together the failure mode and effect analysis together with the calibrated risk graph in order to estimate our target seal, and we have created a report in place to standardize the documentation of these phases. Now let's talk about the phase number 4, the design and engineering of safety instrumented systems. The goal of this phase is to design a safety instrumented system that is complying with the safety requirements specification. The challenge is basically to follow all the requirements that are given by this phase. The first bunch of requirements are related to the design and engineering of the safety instrumented function, safety instrumented system. For example, the hardware fault tolerance requirements, selection of the devices, hardware random failures. The second bunch of requirements are related to the software, to the application program. And the last part of requirements is about the factory acceptance test. In the next slides, I will talk about these 3 types of requirements. And I will start with the hardware random failures. For the hardware random failures, the first thing we need to do is to collect all the reliability information from all the elements of our safety instrumented function, build the reliability model based, for example, in methods like reliability block diagrams or fault trees, and basically after apply the tables and the formulas given by the standard. So with a very simple example of a safety instrumented system with a sensor, a controller, and a safety relay, for each of the subsystems, we need to apply the formulas from the standard to calculate the probability of failure, either on demand or either per hour, depending on the operation mode of this safety system. We have to do exactly the same thing for all the elements of the safety system and calculate the global probability of failure. And afterwards, we have to go to the tables and see if we meet the necessary risk reduction, the target cell. This is the first bunch of requirements. On top of that, the standard tells us that we should evaluate the architecture of our safety instrumented system. Basically, if the probability of failure that we just calculated before is complying with the target seal, we may still need to apply redundancy to our safety system. So basically, the standard provides us a table like this one. And if I give you an example, if our safety function is supposed to be, has a target of seal 2 in continuous mode of operation, we will have a hardware fault tolerance of 1, which basically will mean that we will have to apply redundancy to all the elements of our safety function. However, the standard also tells us that we can use other methods if we have extra information about those devices. One of these methods is the so-called root 1H from the 1508 standard that tells us if you have the safe failure fraction for all the elements of your safety instrumented function, under certain conditions, you could eventually not need to apply redundancy, as you can see here. Basically, it's saying that if your safe failure fraction is bigger than 60% for the type A of devices, in this case, sensor and actuators, you don't need to apply redundancy. And we have similar table for the controllers. So what we have done actually, how we have implemented in our safety lifecycle these 2 requirements, we use actually a commercial tool called Isograph, which is widely used at CERN. The reason is because this tool allows us to create the reliability models in a relatively simple way. As you can see here, we can represent the sensor, the controller part with the input-output cards, the actuator part, and for each of these elements, we can provide the reliability information that the functional safety standards require. Just to give you an example, this parameter right here is related to the safe failure fraction that I just mentioned before for the architectural constraints. Now, the next bunch of requirements, as I mentioned before, is about the software, the application program. The standard tells us how to design, how to implement, and how we should verify the application programs. In addition, it also gives us examples and recommendations. I just extracted here 2 quotes that I consider very relevant for our strategy for the application programs. Basically, they are telling us that the traditional test-based approaches are not efficient enough, and we should apply model-based design in our specifications for the software. Also, it tells us that we should apply a graphical language within the model checking WEBR. And this is basically what we have done. In the adopted solutions, we use model-based design. We use two formalisms, for example, the cause and effect matrix, and we use the sysspec tool that we developed at CERN, or logic diagrams using the GrassEdit tool developed also at CERN. For the verification part, thank you. For the verification part, we use model checking to verify our PLC programs using the PLC Verif tool. In this slide, I will show you just two examples of a cause and effect matrix and logic diagrams for the specification. And the good thing about them is we can simulate, generate tests and verification cases, and eventually code generation. Just to show you the workflow from a specification to verification, from a cause and effect matrix, we can produce manually or automatically our PLC program. We can also generate verification cases and provide these two inputs to our model checking tool, PLC Verif, where it will explore all possible combinations in the PLC program to guarantee that the original requirements are met, and it will provide us a report. Just a few words about the management of the project, the phase number 10. This phase, we have to define the roles and responsibilities of the project members and the workflow and documentation to coordinate them. This is actually what we are doing. This is an ongoing activity for us, and we have created a report in place to standardize the documentation in this phase. Just to give you an example, in one of our projects, our two roles that we have is the functional safety expert and the process expert, that they have different responsibilities within the project. To conclude, we have integrated new tools in the safety life cycle to automatize some of the phases. You can see down in the table the tools with the corresponding phase. We have applied recommended methods from the standard, and we have created a report templates to standardize the documentation of all our projects. As a future work, we will want to keep an eye in the traceability. We will explore commercial tools to keep the traceability between all the phases of the safety life cycle. We will keep working on our workflow flow procedures, and we will investigate further the code generation of our application programs and the integration in our control system frameworks. Thank you very much. If you have any questions, please.
Thank you, Borja. So we open to questions and comments. So I can see WEBR Q&A. So which tool are you using to achieve information about your devices? For example, serial number, calibration date.
Can you repeat the question? Sorry, I didn't understand. Yeah.
You are okay. I can see that question on WEBR Q&A.
All right.
Yeah, you achieve some information from device. So how to do?
All right.
What kind of tool you are using?
Exactly. For the reliability information for the devices, whenever it's applicable, we try to buy certified devices that they come with the reliability information. At CERN, sometimes this is not possible because we have, I will call it more exotic safety systems that we have to use instrumentation that has not been certified by commercial, for example, external companies. So what we can do is use isograph. For example, we use isograph to predict for example, the probability of failure of these devices, the safe failure fraction, and other parameters that we need to apply later in our systems.
Okay, thank you.
This is how we do it.
Yeah. So any other questions? Okay. No questions.
Yes. Do you see this question? What kind of techniques do you use to build your FMEAs, and how do you evaluate the severity of each failure mode? Thanks a lot, and congratulations for the presentation. That's from the questioner.
Yeah.
Exactly. So our FMEA, basically what we do, we have, I will call it a standardized template for all our projects. And basically, we have a group of people participating in the FMEA, bringing different type of knowledge to this to the project. I mentioned before the process expert who really knows the installation. We have other representatives, like I will call it safety experts. In the case of CERN, this is the departmental safety officers who can actually evaluate the different type of risk, like electrical, from cryogenics, and so on. And a representative of, let's say, a functional safety expert that is in charge of applying the functional safety standards. In order to evaluate the severity, this is what I mentioned before about the calibration of the risk graph, is an agreement between the process expert and the safety expert at CERN. Actually, this is one of the most challenging parts of our projects. It's an ongoing work, and at the moment, we don't have an standardized solution. We do it project by project, but we are working in that direction. Yeah.
Thank you. I think we go to the next speaker now.
Yeah.
Yeah. Okay. Our third speaker will talk about the fast protection system for the Chinese spallation neutron source accelerator. Yulang Zhang. Welcome.
Hello, can you hear me?
Yes. Yeah,
Okay.
and we can see your slides. You may want to switch the slides to presentation mode.
Okay, let me start.
Thank you.
Hello, everyone. I'm Yuliang Zhang from CSNS ICALEPCS. I will give you a talk about the fast protection system for CSNS accelerator. This is the outline. Firstly, I'll give you a brief introduction of the CSNS protection systems, and then the design and deployment of the LPS. And the most important part is the logic of beam interlock and mitigation. And finally, a short summary. This is the CSNS facility. The accelerator consists of 80 MeV H- Linac and 1.6 GeV RCS. The beam power is 100 kilowatts in phase 1. The accelerator is 25 Hertz pulsed accelerator. And from the view of PPS, the whole facility can be divided into 3 areas: the Linac area, the RCS area, and target area. And the accelerator have 5 beam destinations. And for each destination, the beam power limit is different. This picture shows the protection system for the whole facility. We have, we have a target protection system and a personnel protection system. This is the PPS is a global system, and the TPS only covers target station and the neutron instruments. And the accelerator protection system consists of PLC-based slow protection system and a LPD-based fast protection system. And both AMPS and FPS used independent keyboard rules to unlock the beam. And the beam stop actuator is on-source timing and on-source acceleration high voltage and the off-cue power source. For the requirement and design rules for the FPS, the response time requirement is less than 10 microseconds, and the FPS should perform the different actions according to the input signals type, and all the interfaces should be fail-safe and can be online real-time checked. And the logic should be as simple as possible and should be developed with reliable tools. FPS should provide software to mask each input channel and provide friendly operating interface. This is a signal classification. At present, the total number of input signals is about 300, and from the power supplies, Linux RF system, and the beam loss monitor system. Because the CSNS accelerate, the 1 power beam loss can be tolerated. So the input signal, are in 2 types. One is the pulse type, and the other is the latch type. For the power supply, the fault signal is usually in the latch type, and for the beam loss monitors, usually in pulse type. And according to the different input signals type, the different actions should be carried out by the FPS. The FPS adopts the tree topology architecture, consists of 3 layers: a signal collection layer, and signal convergence layer, and this mask station for the main logic and the in-log is designed in this layer. All the signals are transmitted from the through the optical fibers. This is a picture. This is a signal collect board, and is the main logic board. And FPS hardware was designed use the VM form as a 6 unit height, and we have 2 kinds of FPS board. One is the main logic board, and the other is the optical signal input board. Both the boards are designed by the CSNS control team. And in this board, there is an embedded event receiver to receive the timing signal. Let's start the logic part. As mentioned before, because the input signals have 2 kinds. One is pulsed, the other is latched kind. So 2 kinds of the beam interlock logic was designed, and different actions should be carried out. One is the mitigation interlock. In this case, when FPS receives a fault signal, and FPS sent 3 signals to switch off the ion source extract timing trigger, and to power to blocks beam gate, and the blocks IF power swing. Usually this 25 cycles, that's 1 second, and after 1 second, the IF power to FQ again, and it's being recovered automatically. This is how the FPS out was generated, because for this, usually this the input signals from the beam loss monitor are the pulse type. Because the electronics of the beam loss monitor does not latch the signal. When FPS receives this signal, the output turn to interlock beam state. This is the high level state, at least for 1 second. And these cycles can be configured as online. Usually we set 1 second. And after 1 second, and the output back to the low level state, and the beam can be extracted from the ion source. Another case is we should shut down the beam, and the beam should be recovered manually. As you can see, it's 2 morph signals. One is to the MPS, the other to signals to switch off the unsourced acceleration high voltage. In this case, if the MPS receives the interlock signal and it will form the RMS, which means the run permit system to switch the motion state to beam off. And for the RFQ power source, if this voltage is less than decreased to less than 5 kilowatts, RFQ power again to RFQ to keep the temperature. Okay, let me show you the how this output signal was generated. It's case one is for the continuous fault signal. When the IPS receives the signal, firstly, the mitigation actions taking place, and if the signals keeps more than the fault signal keeps more than 5 seconds, and the FPS output will be latched to high level state. Another case is for the beam loss monitor input, because the beam loss monitor input is pulse type. So if one pulse is received, firstly, the mitigation measures are carried out. And if two pulse was received in 5 seconds, and the FPS output will latch to high level state, in this case, the machine will switch to beam off state.
2 minutes.
Okay, thank you. And finally, show you the response time. This is the response time measured from the mass station to the unsort trigger was turned off. The round trip is about 2.5 microsecond. So the single trip is no more than 1.3 microsecond. Okay, summary. The fast protection system for CSNS accelerator has been put into operation for more than 3 years, and its beam and lock logic has improved due to the operation requirements. And the response time is much less than the requirements. And the new form hardware is under design and will be upgraded in the CSNS2 project. That's all. Thank you for your attention.
Thank you. Do we have some questions? We have time for a couple of questions. I don't see any in the chat right now, but so I'm interested to know, you already plan for an upgrade. What are the motivations for the upgrade? What will you change?
Because this hardware was designed 10 years ago. We use very old chips. These chips are obsolete. For example, the FPD we use Spartan 6 and other chips we can't purchase now. And the VME bus is also not popular at present. We think we use a newly designed hardware for the HIPS FOFB, and can be used for this fast protection system.
We have one question in the Q&A. How do you check that connection between your system, the master, and devices are okay? Do you shut the beam automatically in such cases?
At present, we can only check the signals from this layer to this layer. This is a SFP collector. We can show each input signal has a heartbeat. The heartbeat is checked with the heartbeat was checked with 1 megahertz signal, and from this layer to this layer, because this is ordinary plastic fiber, so there's no logic in this layer. So the signal cannot be checked. As you can see, there's no chip in this spot.
Mhm. Okay, well, thank you very much. I think we will now move to the next speaker to stay on time.
Okay,
so
thank you.
The next speaker is Fen Tao from Slack, and he talked about safeguarding large particle accelerator research facility, a multi-layer distributed control architecture. Fen, please start your talk.
Thank you, Chair, for the speaker, for the introduction to our speaker. Today, I'm going to talk about the our design for the personal protection system at the Slack National Laboratory. We talk about all kinds of the architecture and also the functional safety concerns. So first, I'll talk about the Slack's accelerator and the safety system at Slack. We have a multiple safety system, and personal protection system is one of the systems for protect the personal safety. And here we argue that a personal protection system function-wise is more like the machinery safety standard, and the setting is more like close to the machinery safety standard of process safety. So we'll try to use a machinery safety standard and try to evaluate our personal protection systems. Then I'll talk about functions and architecture of the personal protection system at Slack. And then I'll talk about, because of the complexity of the PPS at Slack, it brings some functional safety consequence, so especially the safety integrity level kind of concern. So I'll talk about how we evaluate the functional safety, especially the safety integrity level of the PPS, and I'll summarize my talk. Here's the map for the Slack from the Google Map and also from the field. You can see we have 3 beam lines. The one in yellow is the first one we completed in 2009. Is a free electron laser LCS1. The second portion we completed last year is for the high energy physics experiment called FASI2. The one highlighted in blue is the one we are under construction for the LCS2, and it's a superconducting LINAC. And here you can see the white building as our cryo plant. In Slack, we have a near hall here and a far hall here. In the near hall, we have 3 soft X-ray line hatches, and then one hard X-ray line hatch. And then in the far hall, we have 4 hard X-ray line hatches. So at Slack, we have 3 global safety systems. Only 2 of them are classified as safety critical. The machine protection system is important. It's the first one, but it has nothing to do with protecting the people. So that's why we only highlighted the BCS, beam containment system, and the personal protection system as in yellow color indicates they are safety critical. The PPS1 is the earliest system designed at Slack. It's hard shutoff, means like we remove the power supply to the ground and RF. So, and we insert beam stoppers in the downstream. So the overall speaking, the response time is pretty slow. Our design is around 5 seconds. Beam containment system is pretty fast. It uses a lot of similar technology as the MPS. For the LCS2 project, actually it shares lots of the device, especially the beam loss detectors with the MPS. The shutoff response is pretty quick, around 200 microseconds to 600 milliseconds, depending on the technology. 200 microseconds will be based on the purely electronics, and 600 milliseconds will respond to the using safety PLC to initiate the shutoff. The shutoff action for the BCS is pretty soft. It's just close the inject laser shutter and stop the RF. The previous speakers from CERN talk about using process safety standard to in their application, but for the PPS at SLAC, actually we argue our setting is very close to the machinery safety. For example, the picture on the left shows the typical production cells. Here the hazard is a robot arm, and then typical solutions from the industry use, for example, the key bank, the lock, e-stop, micro switch, and the laser scanners to detect the security if the security has been violated and to initiate shutdown. On the right hand side is a layout from our LCS near experiment hatch. We have 3 hatches here, and then each hatch has a dedicated beam line, and one passing through beam line to the fire hall. So definitely when people compare with 2 diagrams, the protection cell is not much different from protection the hatch, experimental hatch, especially hatch to prevent people unintentional access. So actually we use a similar device, for example, the micro switch, e-stop, trapped key, a locking mechanism, a laser scanners, and safety PLC. So they are very close to what we are using in the PPS system. So for example, the first 3 pictures on the right shows kind of safety PLC, different safety PLC we are using for the PPS system. The laser scanner provides CO2 it's a CO2 capable to detect the people approaching the boundary. We have the trapped key bank, and as a safety token when people want to gain the access to the accelerator area. This is a lock we use for interlock with the equipment gate. And this is a circuit breaker we use to shut out the solid state amplifier or the modulator to turn off the RF. All the kind of circuit breaker certified can be used as high as a CO2 level of the protection. The left-hand side lists all the 4 functional safety standard that we directly use or indirectly referred. 6158 is for the hardware development. The 2 standard highlighted in red, 62061, ISO 13849, the machinery sector standard that we're especially interested in when related to this talk. 61511 is for process industry. Definitely, we only refer this kind of standard when we develop the beam containment system. SLAC's PPS design is still not fully functional safety compliant because, again, I mean, accelerator application is very special. We share something in common with the industry, but we also have lots of uniques. Physics driving the PPS requirement. They are not using the risk assessment. Typically, functional safety people are using. For example, our radiation physics, they use a level 1, 2, 3. Try to categorize what kind of the PPS device needed in the field. And then when we get their requirement, we will use a kind of hybrid approach using the calibrated risk graph combined with the layout protection analysis, try to define what kind of the CO levels or what kind of protection levels we needed. And then we further divide this kind of the CO requirement into the 2 different layers I'll talk about later. One layer is access control, because the non-safety rated system, so we only assume it can only take up to 1 CO1 level protection, and the rest CO2 level function, we ask the safety PLC to handle that. Here's the PPS sequence. So basically, how PPS works: lock the door, make sure no people is inside the accelerator tunnel or the hatch. Then we give them alarm. Make sure people really get notice if someone is trapped inside. Then if everything's okay, we will enable those circuit breaker or the switch gear to turn on to allow the operator to turn on this kind of radiation hazard. And then during the when the beam has turned on, if we detect it's kind of excessive, beam loss, and then we'll shut out we'll shut out this kind of radiation device. PPS is a large system because we have 4 kilometers accelerator infrastructure. So it's a global system. Also it's a distributed because of the large footprint. We have over 15 access controller and over 100 safety controllers joined together to complete the personal protection for the SLAC. The overall system can be divided into 5 layers. The top layer is kind of beam program. We have 3 beam programs, LCS1, LCS2, and FACET2. So each beam program has its own global system. We call it the global. And the second layer is the beam switching and the permit. All the beam switching and the permit is carried out in the beam switch yard. In the beam switch yard, because we have 2 beam cells, LCS1, copper linear, and LCS2 superconductor linear, either of the beam can be kicked to the soft X-ray line or hard X-ray line to generate a soft X-ray beam or hard X-ray beam. So the beam switching and permit system respond for judge if the beam line configuration is correct, and also they will be used to driven the permit for those kicker, septums, and beam stoppers.
2 minutes.
Okay, so then the access control, we have responsible access control of the our accelerator. Safety is responsible for the safety control of the zone, and then the sensor portion. Here's a different layers. We use a different technology. Beam program is a distributed, safety. Beam switching is kind of localized safety control. Access control distributed as well. Safety, zone safety, and shutoff system use the local safety control. The problem with kind of PPS is every PPS is modularized to be modularized so that when we need to change one area, will not be changed, will not broadcast to other areas. But there's a problem because, for example, one safety functions, they may not localize. They may broadcast all through the different layout of the controllers and then initiate the shutoff at elsewhere. So it's caused a problem. And it causes the complex in analyze the seal performance. For example, we use a e-stop at different locations. Actually, they have a different shutoff paths. Here's a reliability modeling for different case. E-stop in the near hall is kind of reliability block diagram. If we have some additional, if we have the shutoff explication paths, and then the beam switch permit system will be acted as kind of the diagnostic layer. If he's stopping the beam passing BTH area, more control will step in. This is the kind of case when we go further to the upstream, more and more controller will take action. Here's kind of the signal interflow. For example, if we want to initiate the emergency off at the BSY area, all the controller will be part of the shutoff path. So this causes a problem.
Time's up. Can you conclude, please?
Sure. So problem is kind of we need to be because we have more and more controllers into the kind of shutoff path. So we have to use more redundancy and to make system consistent with the CO2 performance. Yeah, that's all my talk.
Thank you. So we have time for a question. So we have one question. How do you manage the priority of each safety function?
The priority is each safety function is only part of the safety chain. So again, we need to look at the whole shutoff path and then try to make sure the whole safety functions can meet the function requirement and the safety integrity requirement. Each layer is only part of the shutoff chain, not at all.
Okay, I have a question. So how difficult is it? So as you have built first the LCLS1 and then FACET and now LCLS2 to upgrade the safety system as new segments of the LINAC come online, but maintain an operational schedule?
Well, that's part of motivation. We try to use kind of modularized approach, divide the whole system into like over 100 safety controllers so that each piece can be manageable. But as I also mentioned, because this kind of approach, when we go to the project review, every technology is proven and there's no big change to the overall architecture, but the consequence, like the shutoff chain become longer and longer, then we lost the performance on the safety integrity. So that's a motivation for part of this study, why we want to look at the overall shutoff chain, try to see if there's any kind of way to compensate this kind of the safety integrity loss.
Okay, thank you. There's one more question, but we're out of time, so I can ask the questioner to send you a message through Weibo to get an answer to that, please. And we'll go to our final speaker. So before we finish up, I just want to remind the speakers, if your paper is not green in JCal, please attend to that, because I know people will want to read your papers to get more details on what we've discussed today. So our final speaker is from the ITER organization, Damian Abraham Karkinski. He'll talk to us about the integrated supervision for conventional and machine protection configuration parameters at ITER. Thank you.
Thank you. Can you see the screen?
Yes.
Okay. Right. So good morning, good afternoon, and good evening to everybody. I'm here to present this our approach to integrated supervision for conventional and machine protection parameters at ITER. Now, in a tokamak, there are machine protection processes that require high level of integration and coordination between different plants. This translates to high level of configuration coupling between the individual protection systems, which are here for each plant, and also with the way an experiment will be performed. One issue that we have is that we have at ITER essentially two configuration systems. For the plant, this is the supervision and automation system, which is overall a conventional system. This system needs to convert physics values to plant configuration values. For the central interlock system, which coordinates CIS, the central interlock system, which coordinates the central coordination modules. This is the CIS supervisor module. This system has requirements limited to individual threshold and Boolean values. This is simpler, but still there is thousands of parameters. It's not a simple system in itself. Now, another issue is that all protection functions within ITER have 61508 rated reliability requirement. The only difference with functional safety, however, is that the level of assurance for the machine protection function stops with the Director General. There is no external stakeholder to satisfy here, like a country nuclear facility, nuclear regulation body. Now, we need an integrated configuration mechanism between the two systems. And we cannot, of course, duplicate the configuration mechanism in terms of extremely 61508 compliant and conventional. This would imply a massive overhead in managing massive amounts of data sources. And so we've opted for a different approach to identify the gaps in compliance with the conventional system, that is SUP, address in an integrated manner, and provide a central technological solution to use in all plants. This slide presents the simplest example of a configuration parameter coupling that I could muster. In the first case, we have an experiment where we'll run at 15 megamps, so the plasma current will have to reach 15 megamps. The toroidal field will be 5.3 Teslas. And in the second example, which is what we call a dry run. There is no plasma, 0 megamps, but we're still operating the magnets, and the toroidal field would still be substantial. Now, the requirements on the central interlock system can be thought of as one big invariant at any point in time. In the first case, whatever the environment is, and we want the magnetic diagnostic to be fully fault tolerant. We would not want to start the pulse unless the magnetic diagnostic, for example, does not show that it is fully configured and fault tolerant. And during the pulse, if there is a degradation in that diagnostic, we want to immediately issue stop to the pulse via various methods. Now, in the second case, of course, we can be much more lenient. We can only require those subcomponents that are being, for example, commissioned to be active, and the rest and the pulse can continue. And so you can understand that the parameters of the pulse schedule in a very big way affect the desired investment protection behavior of the central interlock system. Now, on this slide, as I said, the configuration of the magnetic diagnostic, for instance, is done through SOUP. And this is through a chain of steps arranged in a workflow. The steps can be transformation steps, taking data from sources and then computing and then crunching them down to, for example, from floating point to fixed point for the use in FPGAs and this kind of stuff. Or they can be verification steps. So in this particular case, the weights for the magnetic sensors are checked against historical data, checked against models of their behavior, such that we can ensure that the calibration factors are not out of bounds and would produce results that are erroneous. Now, this slide does not show all the parameters that we'd like to check. For instance, we would like assurance that the data source was authentic. For instance, we will check if the data source, the data was intended to be used, the data that was intended to be used for a pre-commissioning pulse is indeed used in a pulse for pre-commissioning and not vice versa. We could make a mistake. We could use data that has not been commissioned properly and try to run a 50 megaamp plasma with unknown parameters. Okay, and the problem is that ITER operates fully autonomously once the pulse is loaded, and after loading these parameters to the system, all operation is fully autonomous. And so I'll note that this workflow does not actually check by itself whether the plant can be modified at a particular point in time, such as the current ITER operational state. This knowledge is stored with the right guarantees only within the central interlock system. Now, the central interlock system has a slightly simpler configuration mechanism, but it is 61508 compliant. We call this the high integrity operator commands protocol. It is an application layer protocol that is built on top of the black channel principles in the 61508 standard. And this means that there is a sort of standardized FMEA through the 617843 functional safety field bus standard. At the messaging layer, it implements various measures like controller ID, function ID, sequence numbering, timeout, and feedback in order to guarantee a 3-step verification process, which ensures that the controller being modified is as intended by the operator, the function being modified is as intended by the operator, and the value being changed is as intended by the operator. Parameters are loaded in a staging. Parameters are loaded in a staging area until the 3-step verification process is complete, is established, and then they're moved into the critical path of the plant. So in order to find the right integration points between the plant configuration system and the central configuration system, we had to review the configuration schemes against 615083 requirements, particularly also Annex G, which is non-mandatory, but it's still very useful. SUP was classified as a T3 support tool in this case because it can affect the execution of a PIS. PIS editor can be can have fully data-driven interfaces and configuration parameters. So we need to cope with any complexity here. And we come up with the following requirements distributed across the three systems. So SOUP, of course, will execute workflows consisting of verification and transformation steps. It will log all inputs, outputs, rows per workflow and per step relating to, thus relating data sources to final loading actions of parameters to a PIS. It will implement verification and transformation steps at various predefined levels of integrity, and it will digitally sign outputs with a hash. The CIS will mask parameter changes of a plant at inappropriate time, operate related interlocks to a state where the plant can be modified, transfer the hash from SOUP to the PIS via HIOC, which is secure, issue the necessary administrative information to manage HIOC, and it would lock the hash and seed to link the parameter change request to a particular workflow execution in SOUP. So we will be able to ensure complete traceability from the final loading of the parameters to the data sources. The PIS will have to, the plant, we call them plant interlock system, essentially, will define workflow requirements from a risk analysis on configuration needs, define integrity level for subtransformation and verification, provide an interface to mask parameter changes at inappropriate times with HIOC function, and after unmasking, set functions to unavailable. And essentially also, depending on technology and on criticality, provide runtime verification over the final parameter storage in its status monitoring. Now, an important point to point out is that we don't require the whole of SUP to be at the highest integrity level, which is still 3 in our case. If that were the case, SUP would be just simply too expensive to develop. There are many patterns that we can consider, but here are just 2. In the first case, outputs are digitally signed, and then they can be transformed across codes and interfaces of unknown pedigree until the necessary assurance is reestablished at the other end by checking the digital signature. In the second case, the verification steps may be not required, not the required, individually may not be the desired integrity, but combined, they provide an increased level of integrity because they could be implemented using different methods. Sorry, they could be implemented using different methods, implemented using different implementation languages, and they could even be developed by different teams. So overall, and I'm like to finish here, is that our integrated strategy looks something like this. SOUP will digitally sign its outputs and send the digital outputs to the CIS. If the plant can be modified at that point in time, SIS will relay the digital signature to the PIS, telling it to disable the protection function and to expect a new parameter set. This action is confirmed to SOUP and to the PIS, prompting SOUP to send its main configuration parameter set to the plant. And the plant will then eventually check the parameters against the digital signature, which it receives through the CIS. And if it's correct, it would apply it into the critical path. The important thing about using this hash is that it maintains the simplicity of the SIS supervisor module parameters, but this hash applies to parameter streams of any length and any complexity. Thank you very much. This is my conclusion. So we've presented our integrated approach based on 61508. It solves the complexity issues of operating a tokamak. We have to be mindful that 61508 is a Go-based standard. There's no really compliance per se. You always need to be sure how you are addressing a particular goal and what is necessary and sufficient to meet this goal effectively in a particular case. I'm afraid
I'm going to have to stop you here. We're out of time, but thank you very much. And if you have questions for the speaker, please contact him directly. we're out of time for the session now. The ICALEPCS Awards are held in the other virtual conference room L, if you want to switch over to that, starting in less than 1 minute now. Thank you, everybody, for attending, for questions. Thank you, Shoji, for co-chairing. And I hope you enjoy the rest of the conference.